Hi, my name is TJ Flynn. I'm an acoustics research scientist at the Johns Hopkins University Applied Physics Lab, and today we're going to talk about Python and distributed acoustic systems. Right now, we're going to start off in Jupyter Lab or Jupyter Notebook. Hopefully, you all have had an opportunity to set that up. We're here in the main screen, and we're just going to go ahead and get started. So we'll click on the DAS_tutorial Python Notebook page. We'll open this up, and this is where we're going to do all of our work today. So a little bit about this tutorial, what we're going to go over. We're going to go over an overview of what Distributed Acoustic Sensing, or DAS, is. We're going to talk about how to ingest some DAS data and then process that data. We're going to talk about making some environmental inferences from the signal processed DAS data, and then we're going to attempt to validate some of those inferences through other available data sources that aren't the DAS array in question. So that's going to include some HICOM, meteorological forecasted data, as well as actual measured NDVC buoy data. And I also want to mention this tutorial in itself was informed by a number of other things on the internet, particularly a tutorial by Ethan Williams, formerly at Caltech, and I think currently at University of Washington, who had a tutorial that was very useful for getting me started into looking at some of this stuff, as well as some of these other references down here. And so at this point, if you don't know what distributed acoustic sensing is, don't worry, it's pretty new. So what is distributed acoustic sensing? DAS is a pretty new measurement modality that allows us to capture acoustic signals along a spatial extent, or an array that stretches out over some long distance. And if you're thinking, how is that different than a typical acoustic hydrophone array? It's a great question. In concept, at a high level, it's pretty much the same. We have this cable that goes throughout the ocean, and different parts of that cable are sending back information about the acoustic signals that are impinging on that section of cable, much like a hydrophone over an array will record data corresponding to where that hydrophone is located. But the physical mechanism behind DAS is a lot different than a typical conventional hydrophone array. So for DAS, what we have is a long fiber optic cable, and this fiber optic cable is constantly being pinged with pulsed laser light that travels up and down or down and back the cable pretty fast. The whole time it's traveling down, it's constantly hitting these little impurities in the fiberglass or fiber optic cable that backscatter some of the energy back to the original interrogator or modem. The crux of this is that backscattered energy has encoded in it information about the acoustic energy impingent on that particular section of cable at any given time. Because as an acoustic signal hits the cable, it causes the cable to expand, breathe and contract, or strain, and that strain modulates the phase of the backscattered energy. And what's more is that you can look at the time it takes between sending the original laser pulse to receiving the backscattered pulse to know where along that cable a signal is coming at any instance in time. And so what that can allow one to do is to take this cable, ping it with laser light, and break it up into kind of discrete segments, or what we call channels, much similar to a hydrophone on an acoustic array. And so you can generate images like this, where you might have channel number, which is effectively distance along the DAS array on one axis and time on the other, and you can start to infer useful information about your environment. We'll see what that looks like here in a little bit. And so how is this, what opportunities does this present over typical conventional acoustic measurement devices that have been around for 60, 70, 80 years in some instances? Well, some of the potential benefits of DAS is that there happen to be a lot of fiber optic cables already strewn across our oceans. We all use the internet. You're using it right now, and telecoms and the internet require these transcontinental cables. You can see here, as a picture pulled from a New York Times article, shows that there are a lot of cables in the ocean, and a lot of these cables could be leveraged for telecom or for acoustic sensing purposes to effectively monitor large swaths of the ocean. And to do this with conventional arrays would be exorbitantly expensive. It's already billions of dollars of infrastructure as is, but the idea is that DAS could allow us to leverage this existing infrastructure in a new way for acoustics and overall environmental oceanographic science. And so we're going to look at some DAS data from a particular cable or a particular system. The DAS system we're going to look at is data that's been made available through the OOI, or the Ocean Observatories Initiative. This data comes from a particular array called an OptiSense array. And so there are two of them as depicted in this plot from the OOI's page. If you click the hyperlink up there, there's a north cable and a south cable, and we're just going to be looking at the north cable right now for the purposes of this tutorial. And so the data come in these 60-second snippets that were collected sometime around 6 to 9 a.m. one day in November of 2021. Each of these 60-second time snippets essentially consists of channels that go all the way from the interrogator at Pacific City, the screen block, out to this offshore interrogation limit that's about 60 kilometers due west. And it's broken up into roughly 2-meter channels. There are thousands of channels here, and each 60-second data snippet is about 800 megabytes. So 800 megabytes per minute DAS for one cable. DAS is a pretty data-intensive storage demanding approach. But there's a lot of great information there, and we're going to look at some of that. So at this point, we'll go on and move to the Python portion of this. The very first thing here is we're going to need some libraries, some pretty standard but not built into Jupyter Lab Notebook Python libraries. So you might need to uncomment and install these various things here. But once we do that, we're going to import some useful and common subroutines and libraries. The first one's H5Py. We're going to use this for importing HDF5 files. That's the data format of our DAS data. We're going to pull in NumPy for general array processing, SciPy for some signal processing, some plotting stuff, some pretty plotting stuff for color maps. Pandas is going to allow us to import some data. And then we have date time, which will allow us to use some of the date time encoded UTC data in the DAS format. And then Pickle here will just allow us to import or load in some data that was previously saved out through Python. So the first thing we're going to do is we're going to actually ingest some DAS data. So with this repo, we have some DAS data here. It's this folder or this file over here. We can see in our little browser window. And you can see it's about 784 megabytes. So we're going to go ahead and run this section of code. We'll shift enter. And what we did here is we have used the H5Py or the Python HDF5 format reader to pull in this, this database. So what is HDF5? So HDF5 is a hierarchical data format. It's a very convenient format because it's simple, easy to interpret, and there's libraries for it in pretty much every common language, MATLAB, Python. You can do it in C++. And H5Py is the library that allows us to read this. And it's pretty simple. We just give it the file name here. We use this function with R to read. And now we pulled in this large database's worth of data. This here does not hold all the data, but it will allow us to point to and extract the data later. We can actually print out the keys, which are some in HDF5 lingo, what we would call groups, but in Python we call them keys, which are effectively the names of these groups, which are like folders within this HDF5 file. And so we can see here at the top level, there's only one folder, and it's called acquisition. But we can dive further down into that. So if we run this line of code here, or this little comment or code section, we can look at all the attributes that fall under this acquisition folder. So we see there's an acquisition ID, gauge length unit. And so there are a lot of things under this folder that we can plot out. So here we have a print statement that allows us to pull some of the values out of this database file and plot them. So for instance, we can show here that the system gauge length, which is effectively the time length that the laser pulse ends up creating as it traverses down this cable, is about 51 meters. The pulse rate of the system is 1 kilohertz, and the spatial sampling interval is 2 meters. So it's actually about 1/25 of the gauge length because you can kind of overlap the gauges. So now we can see here how we can use H5Py to get the database and access some of it. So let's start looking at some actual data. So in the acquisition group itself, this kind of parent folder, there's two subfolders. There's a custom and a raw. And the custom has some information about the parameters of the DAS system. That includes some information about how the times are synced, some information about what the refractive index is. And then the raw zero, this is where our actual data are. And within the raw zero group, which itself is a subgroup of acquisition, there are even more subgroups. So within the raw zero, we have a custom, which is different than the custom above it, raw data time, and then raw data. So this is essentially just like File Explorer in Windows or in any of your OS of choice. We can have folders. Those folders can have files, or they can have more folders in them. So we just need to know what the format is, which you can use by essentially using these key functions. And once you know them, you can pull them out. And so what we have here is first we're just going to pull some of the data in, and we're just going to plot it. So we're going to do raw data here, which is going to pull from the acquisition group, and then we're going to pull from the raw subgroup of that, and then we're going to pull this thing here, which is raw data, which is an actual set of data. So we're going to point to this and pull the data out of the H5 file, and then we're going to plot just the time series for one arbitrary channel. So there are tens of thousands of channels here. We're going to pick channel index 3141, and then we are going to take that slice of the raw data array, and we're going to plot it here. So we create a figure. We're just going to plot it. So we don't have any X data. It's just straight up Y data. So it's going to plot the value of each element versus the element index, and then just some labeling down here. So when we plot this, what we end up getting is this figure right here. So this is good. So it's not a flat line, and it's not a bunch of noise. This looks like something. And what we have here is we have some raw, unnormalized data for one channel that goes from 0 to 12,000 time samples. Of course, we would actually like this to be in time, and we would like this arbitrary raw data amplitude to be in something physically meaningful. So now what we're going to do is we're going to move on to normalizing the data and getting the actual physically meaningful data. And so the amplitude of the raw data is not in units of strain, which is the natural unit that is typically reported for a DAS system. It's still in units of what we'd call unwrapped optical phase, which is just what this modem happens to record it in. But the point is we need to convert this to strain. And so we can do that by via this relationship here. And I won't go over all this, but to say that there are some good references, particularly the second reference, Lindsay and Martin, has some good information on it. But what we're building in is we're building in information about the gauge length, the index of refraction, the wavelength of the laser. So this strain is effectively in wavelength divided by some non-dimensional stuff, and then a length here times radians. So the strain itself is non-dimensional, as it should be. And so this is what we want. Now we need to get some of these parameters put in here. What is the gauge length? What is the index of refraction? And fortunately, those parameters are also hidden in the original DAS folder or DAS file. So we can define some DAS parameters here. We can pull in the wavelength, the gauge length, the refractive index, and this Pockels coefficient. We can put all these in DAS parameters. So this is a Python dictionary. It's very similar to a MATLAB struct, where we could call from it by just using these names, which give us these values. Okay. And then we can move on and pull some other useful information, the sample rate, the channel spacing, the number of samples, and we can go in here and compute we can also compute the strain scale factor, which is this guy up here. And now we can actually create a dictionary for our DAS data, which we ultimately want. So in here, we're going to put in our sample rate, our channel spacing, the number of time samples, and the number of spatial channels. We're going to have a time vector, a distance vector, a two-dimensional strain matrix, which is just our raw data times the scale factor here. And then we're going to also just append our parameters. So we've essentially put a dictionary inside of a dictionary. So it's like a folder in a folder. So we'll go ahead and run this. And nothing popped up, but it ran, so we can move on to the next. So now that we have the data in hand, let's go ahead and start analyzing. So the first thing we might want to do is plot some time series for a few particular points along the array, and then perhaps also plot the power spectrum or the frequency dependence of the energy in each of those channels. So So what we're first going to do is we're going to define a frequency vector using some NumPy functionalities. And then we're going to pick some channel ranges here. So we'll pick 5,000 meters and 40,000 meters along the cable. Then what we'll do is we'll go in this for loop for these various subplots. So we're going to have two subplots, one for the time and then one for the frequency domain images. And for each of the channels, we're going to first get the index of that distance. So we're going to look at the distance vector and see, okay, which index of the distance vector is closest to 5,000 meters. That gives us the index, and we then want to use to get the channel data. And then once we get that channel data, one important thing that we have to do here is you have to detrend it. So the channel data itself will have some kind of arbitrary average value, because as these DAS cables are put out in the ocean, small temperature fluctuations cause the phase to just ebb and flow. And that gives us some offset that we can't know generally ahead of time, but we can remove from the data with a basic detrend. It's just subtracting out the mean value for each channel. And then we can compute the power spectral density by essentially just taking the Fourier transform of the time series that we just generated, and then we're just going to plot it. So we're going to plot the time series, and we're going to plot the power spectra, and then we're just doing some axis labeling and setting the frequency scale to a log scale. So we can go ahead and generate this. Let's see. All right. So we have two plots here. So we have, again, time and frequency on the left and right plots respectively. And in blue, we have our 5 kilometer, and orange, we have our 40 kilometer channels. So one thing you can see right off the bat is that even just with the 60 seconds of data, we can tell that there's some interesting stuff going on. The distance along the cable generally affects what you see. So we have larger intensities at the close near shore channels and lower intensity generally in the further and more distant channels. But we can see in this, there's a lot of there's a very particular kind of low frequency energy here in the blue 5 kilometer channel, and we see less of that in the orange. If we look over in the frequency domain, we can see that, we have a big hump down here at about 0.1 hertz for the near shore component. As we get further offshore, we see our frequency peak kind of shifting. And then we also see this higher energy stuff that's happening out, at and above 10 hertz, all the way up to the max frequency that we can observe at, which is half the sample rate here, which is 100 hertz. We could also come in here and instead we could comment out this line, and now we'll have a few more channels to look at. So in this case, now we have 5, 10, 20, 30, and 40. And it's kind of the same thing. We see that near shore, we have overall higher amplitudes, but we have this fine kind of higher frequency information that we can easily see here at the distant channels. But we'll look more into this as we go through. So even just with that, we have some information about what we see here, but it's hard to tell what's generating this data or what's generating these signatures, so to speak. And so we can delve a little bit deeper into this by doing some space-time processing. Specifically, we're going to plot the data both in space and time, and then using the two-dimensional Fourier transform, we're also going to plot it in the wave number frequency domain. And so what we're going to do is we're not going to plot all of the data along the channel, but we're going to pick out a 15 kilometer region from 35 kilometers to 50 kilometers, and then we're going to take the full 60 seconds here. We're going to find the indices that essentially give us these values. We're going to downsample by a factor of 10 in space just to make things a little bit more computationally simple. We're going to define our sample rates here. And then ultimately, we're going to pluck out this matrix or this array called strain, which is going to be a downsampled block of the larger data set here. And then so we get that, again, we're going to detrend it. So we're going to subtract the mean out of all the channels, simple as this one line of code. And then we're going to compute our frequency and wave number vectors. And then we're going to take our strain data, do the 2D Fourier transform of it here, and then ultimately plot it in decibels. So we have this 20 log 10 going on here. And so a lot of this might seem, unmotivated, but if we plot it and look at it, we can see why we might want to do this. All right, so we just ran this, and first thing, we're not plotting anything yet, but we can look here and see the shape of the strain and the shape of the Fourier transform strain arrays are the same, which they should be. And it's in units of channel number by time sample. And we can go ahead and plot these things too. All right. And so now we've got two plots. So at least something happened here. We've got our 60 seconds in time versus our 15 kilometers in distance along the cable here. And we can see that we get some interesting kind of structure in here as this kind of like oscillation, sinusoidal, so to speak, data signature is here. If we look over into the K omega plot, it is a little uninteresting, but part of this is because we need to be careful about what units we're plotting or what axis limits we're plotting here. So we're essentially plotting the whole axis limits, but if we were to zoom in on a particular portion of this, we can get some more information. Aha, so we zoomed in on the x-axis, which is frequency, and on the y-axis, which is wave number, and now we have some structure that we can see. So if we're looking at this, immediately I can kind of see some stuff. We see these big swooping like kind of parabolas. It almost looks like there are two. And then if we kind of get closer to this zero frequency axis, we can see almost another parabola hidden here. And so the wave number frequency spectra showing us some parabolic structures super suggests that we're looking at propagated energy that's coming from some wave dispersion. And if we're in the ocean, perhaps the most reasonable thing to guess at the first sight of this would be surface waves, because surface waves or surface gravity waves, essentially waves propagating along the surface of the ocean that we're all probably intuitively familiar with, follows a quadratic dispersion relation. So the frequency squared goes with the wave number times gravitational constant. And so we can take what we just had up here and plot it again, but now we're going to add in the theoretical parabola for a surface wave dispersion. So we'll plot this. Aha. So we have the same time space plot, but now our frequency omega or frequency wave number plot has this theoretical curve, which matches very well with this theoretical, or the theoretical curve matches very well with the measured data for this parabola here in the center. Now, of course, there's another parabola out here, and we'll get to that in a minute. But the idea of this other set of parabolas that are out further away from the y-axis is that since these are higher frequency, and since phase speed is essentially just frequency divided by wave number, these parabolas correspond to waves that are traveling much faster than the surface gravity waves. As it turns out, these are actually going to be something called Schulte waves, which are waves that travel at the interface of the seafloor and the water column at the bottom, and they travel quite a bit faster than surface gravity waves. But they still follow a dispersion relation, which is a bit more complicated than just omega squared, but we can see it here. But before we move on any further, we can also see that we have some kind of strong vertical and horizontal artifacts here. And as it turns out, these artifacts are going to have to do with essentially side lobe effects from our Fourier transform. What that means is that the Fourier transform, the fact that we're looking at a finite chunk of time and finite chunk of space data, we're getting effectively side lobes that correspond to truncating our data. We can clean this up a little bit by using window functions, both in the time dimension and in the spatial dimension. This whole thing is called apodization. That's the $5 word for it. But effectively what we're going to do is we're going to do the exact same thing we did up above, but now we're going to define a two-dimensional window function. So we're going to define an array. It's an outer product of here a boxcar window in space and a boxcar window in time. So we're going to take this and we're going to plot it, and we're going to see what happens. All right, and our plot looks the exact same. And that makes sense because a boxcar window is effectively just a window that's all ones. It's a uniform window. It's effectively the same as not using a window at all. So instead of using a boxcar window, we can comment this out and then comment, say, a Hamming window. And all this is doing is it's going to take our data and kind of taper it, decrease the value of our data toward the edges. And that makes it smoother at the edges, which reduces the side lobes. And now we get a picture that looks like this. There's still, some that we see the same structure, but we see it with a little bit less side lobing, and it just looks a bit crisper, even though technically the resolution dropped a little bit, but it just looks crisper. So this is good. And the next thing we can do is if we wanted to see, say, what the data looked like without this low frequency surface gravity waves in it, we could also apply a high or low pass filter to it. So here we have the exact same thing that we just did before, but now we're going to take the data and apply a Butterworth filter here, which first we do by defining the filter. So we say we want a high pass filter, and with this high pass filter to filter out everything below 0.3 hertz, and it gives us some filter coefficients that then we use in the linear filter function here in SciPy. And so we can run this, and what this is now going to do is it's going to filter all that low frequency surface wave energy out of our signal. And so now what we're left with in our space-time plot, or time-space plot, is effectively just these higher frequency, faster Schulte waves, or these seismic waves at the seabed. And so we can see it looks a bit different. We still have the structure, and our K omega plot has this big, cavern in it now where we've essentially filtered out this low frequency data. You could also come in here and comment out the high pass and put a low pass filter in there, in which case it'll give you only the surface waves, but I'll leave that to the reader. And so now that we have looked at this, we can actually start to make some claims about it. One claim that we might make is that if we go back and look at the data here, we can see that the Schulte waves, if we limit ourselves to looking only at the right side of this plot, which is the positive frequency component, we see that the Schulte waves have more energy here in the negative wave number, or in the bottom right-hand corner, than they do in the top right-hand corner. Conversely, the parabola here that corresponds to the surface-generated waves, or surface gravity waves, has more energy. It's kind of this asymmetric parabola, has more energy in the top right corner than it does in the bottom left corner. Because of this, what this actually implies about the array is that surface gravity waves are traveling down the array. So the surface gravity waves that we're picking up here for this minute of time are traveling out toward the west, away from shore, whereas the Schulte waves are actually traveling out more closer to due east, although there are Schulte waves kind of traveling in both directions. And so this is kind of a claim that we can make, which perhaps is interesting, but can we vet it with any other data? So what we're going to do here is we're going to look and compare our results to some other data sources, namely HICOM, which is a meteorological forecast that includes, among other things, ocean currents. And then we're also going to look at some measured buoy data for a buoy that's not too far away from the DAS source. But before any of that, we're going to make some plots that will help us later on down the road. So first, we're going to plot the geographic location of the DAS array, kind of similar to the plot that we showed earlier, but we're going to plot the bathymetry, and it's going to allow us to overlay some other stuff on it. So for the bathymetry, we're going to use the Jupyter bathymetric database. You can follow these links to find it yourself. The Jupyter database is like 7 gigs, so we didn't want to put it in here, but if you did have it, if you did follow it and get it, this code would work for you. In lieu of using this code, though, we've already pre-saved some of the data. So if we run this little code snippet, we will now have read in, using this pickle toolbox, we've now read in a dictionary called BAPI, which has the following keys in it: latitude, longitude, and elevation. So a vector, and a two-dimensional array. And so we can also go and get the dash geometry from a file that we pulled from the original OOI web page, which you can follow here and get for yourselves. And that's just a text file. And because it's a text file, it just has, in this case, 2 columns, which are the latitude and longitude values for points along the array. And we can easily read that in by defining the file name and then using pandas, this PD here, pandas, to essentially get the data in as a list, and then NP array to turn it into a NumPy array. And then we can print that. So if we run this, this is our list of coordinates for the array. This is nominal. One of the hard things about DAS arrays is it's hard to know exactly where it is, but this will be good enough for us. And then we can take this and we can plot everything together. So we'll plot the bathymetry and we will plot the array. So here we are effectively looking at, the west coast of Oregon. We got Portland somewhere up here. We got Pacific City kind of at the terminus or at the beginning of this array, and then the array goes out due west. So when we talk about close or short distances, it's near the coast, and long distances are out further west. And what we think here is based on the data that we've got currents, or we have surface waves moving toward the west down the array. So one of the things we can use to try to validate that or check that is HYCOM. So HYCOM is a publicly available global ocean model that's constantly being computed and updated every day and assimilated with measured data from buoys, floats, XBTs, which are sound speed profile measurements, satellite swaths of the ocean surface. All of these things go and provide forecasts very similar to like a weather forecast. And of the various products that HYCOM provides, they provide currents which are not actually just at the surface, but go all the way down the water column. And they provide north-south currents and east-west currents, and with both of those, we can figure out the direction of currents as predicted for this date in November of 2021 from HYCOM. So we already went and downloaded this HYCOM netcdf file. Netcdf is the file format of HYCOM here. So we already went and downloaded that. That is right here, UV3Z is what it would look like if you downloaded it yourself. And you can do that using the online GUI here. Now, HYCOM files are netcdfs, which isn't the same as an HDF5 file, but it's actually based on HDF5, and it's convenient for us because we can use almost the exact same formatting to ingest the HYCOM data as we use for the actual DAS data, which is HDF5. So we'll run this line of code here, where we just give it the file name. The HYCOM file, we just use H5Py. We can print out the keys. So in the HYCOM file, we have water_u, which is the horizontal component of the current, water_v, which is the vertical, or I should say latitudinal component of the water, lat, long, time, and then depth. In our case, we're actually only interested in the surface currents, so depth doesn't really matter for us. And we can also take this and put this into its own dictionary, much like what we've been doing before, where now we have currents, we have the latitude, longitude, and the water, and the latitude and the longitude directions, which are 2D NumPy arrays. So we can go ahead and take this and plot the same thing that we just did before, but now we're going to add on top of it a quiver plot, which are arrows that point in the direction of the current over the full map. So we can go ahead and plot this, and now what we have here is essentially a quiver plot, which shows actually, if we look at HYCOM or HYCOM's forecast for this data period that we were looking at with the DAS array, it does indeed predict that or suggest that currents at the surface were traveling generally due west along this array at the time of the sampling. That's nice. It looks nice. But HYCOM is only a forecast. It's based on data, but it's not measured. And beyond that, surface currents in HYCOM aren't actually the same as surface wave directions. So while this is a good surrogate or maybe a good inkling, it would be nice to compare to measurements. And that's where these NDVC or National Data Buoy Center buoys come in. So NDVC catalogs data and stores data from like 1,000 buoys over the earth. If you click on this link, you'll see a map of all the buoys. We can find one buoy number 46248, which happens to be a bit north of the DAS array, but it has data for the wave direction as measured at the same time of the as the data collect. And so you can find that exact file here at this link, but we've already loaded it in. That is this file right here. And the nice thing about this is the NDVC data, much unlike DAS, is it's pretty small data file sizes. So a year's worth of data here is like on the order of a few megabytes versus a minute's worth of data being 800 megabytes for DAS. So the point is, with the NDVC data, you can pull it in as just a text file. We can actually look at the text file if we wanted to. Let me see if I click on this. And the text file here is essentially just a bunch of columns. And so each row is a particular date, and we have a year's worth of data in 10-minute increments. And we have wave direction, we have wind speed, we have significant wave height, and then we have some other stuff that won't matter to us, but does exist. And so what we can do, again, because it is a text file, we can use pandas to pull in the data as a list, and then use NP array to make it an actual array. And then we can just check ourselves by plotting or printing out the first row of the data. So we see 2021 is the year, and then 1 is the month, that's January, so this looks reasonable. Now we're going to need to do a couple things, like any good data snipping or data snooping. There's going to be some corrections you got to make. We're going to use significant wave height later, and significant wave height, for whatever reason, on these buoys is only measured every 6 measurements, so it's measured hourly as opposed to all the other rows, which are every 10 minutes. So we're going to take every 6th value from this array. So we're going to start at value 5 and take every 6th value. So now we'll have hourly measurements throughout the year 2021. And then we're going to convert the essentially year, month, day, hour, minutes to date times, which we can use this. And so now we'll have a vector of date times for each of our measurements. And like we've been doing, we'll put that all into a dictionary that includes information like the buoy number, the lat long of the buoy, the date vector, and then vectors for wave direction and significant wave height. So we can go ahead and run that. And so the first thing we'll do here is we'll just take the latitude and longitude of the buoy, and we'll plot that onto the plot that we already made. So it's literally nothing different than what we've done before, but we're plotting one scatter point on top of what we plotted before. So we'll plot this, and we see that this white dot here indicates where the NDVC buoy is. It's a bit north, but it's one of the closer ones available. And then the last thing that we'll do is we need to take the date time from the DAS file, essentially the date time that corresponds to the raw data that we were measuring and that we're looking at, and find the closest date in the NDVC buoy data file. And so we can do that by first taking and getting the DAS date time here, so it's a singular date time, and then we can essentially look at the minimum argument or the minimum difference between the array of our NDVC date times and our DAS date time. So we'll do that here. It's going to give us an error or a warning, which doesn't really matter. It still works. And now what we're going to do is we're going to take that nearest buoy time here, and we're going to use that to plot the wave direction on our plot. So we're going to essentially figure out the wave direction at the time for the NDVC buoy that's closest to the measured DAS time back in November of 2021. So we can run this, and we see that this white arrow here, singular quiver, is pointing in the direction of the wave motion from this buoy at the time that DAS data were collected. And like we saw before, it's generally trending to the west, which is favorable for our analysis. Ultimately, this isn't incontrovertible evidence to our claim that the surface waves are going due west, but it is supportive, and we can further drill down to this by looking at more minutes of DAS data, looking at the other DAS array, the south array. We could also pull in information from more non-DAS systems. We could look at the global forecast system, which gives us wind data historically. There's a number of other things that we could do. And lastly, since we have a year's worth of NDVC buoy data already loaded up, we can actually generate a scatter plot of the significant wave height versus wave direction for all the data points within that year. And we can see if the data point that we drew is like a statistical outlier, or does it fall reasonably well within all the other points along that year. So we can do that here. We're essentially just making a figure in a scatter plot where we're plotting wave direction versus significant wave height on the y-axis. And then we are overlaying the dot that we determined was the closest one to our DAS data time. And so here's the plot essentially hourly throughout the entire year of 2021. And we see that the data point that we took is like right in the middle of this cloud. So probably not an outlier, probably a little bit more suggestion that the wave direction is generally traveling due west, at least in this part of the Pacific Northwest. So that was a lot, but that's everything we got here for DAS using Python. Again, don't hesitate to reach out if you have any questions about this. Otherwise, get to snooping. There's a lot of things out there to find. Have a good one. Bye.